Okay, so get this. The estimated production cost of an iPhone X is roughly $412.75. That is actually about 59% cheaper than its starting retail price of $999. Kind of makes you wonder, right? How does a massive company like Apple accurately estimate all those costs, balance future revenues, and set a price point that basically guarantees a profit? Well, the answer lies in a really foundational concept that drives literally every single major financial and engineering decision. It's all about understanding how the value of money fundamentally changes over time. Welcome to this explainer. Today, we are completely unpacking Chapter 4, the time value of money and economic equivalence. We're going to build you a comprehensive toolkit to help decode these exact kinds of complex financial realities.
Here is our game plan for this explainer. First, the time value of money. Second, mapping money with cash flow diagrams. Third, determining economic equivalence. Fourth, arithmetic and geometric gradients. And finally, number 5, real-world bond valuation.
All right, let's jump right in with Section 1, the time value of money.
Imagine a scale. On one side, you have a clock representing time, and on the other, stacks of cash. This brilliantly simple visual captures the core philosophy for everything we're talking about today. The absolute golden rule of engineering economy is this: a dollar in your pocket today is worth infinitely more than that exact same dollar 1, 5, or 10 years from now. When you commit capital to a big project, that money is usually tied up for a long time. So this scale is a great reminder that time and money, they're permanently linked. But why exactly does that scale tip?
Well, there are two main reasons money has a time value. First up is earning power. Simply put, money can be put to work to make more money over time. If you have cash in hand right now, you can invest it to generate a return. Second, we have inflation. This means your actual purchasing power actively changes as time passes. We all know a dollar buys way less today than it did 20 years ago, right? Now, the financial market measures these two opposing forces, earning power and inflation, through the interest rate. Interest is basically the tangible, real-world manifestation of time value. It's the cost you pay if you're borrowing and the profit you collect if you're lending.
Moving right along to Section 2, mapping money with cash flow diagrams.
A cash flow diagram is, simply put, a graphical representation of cash transactions over time. I absolutely love these things because they are essentially financial treasure maps. Instead of getting bogged down and lost in massive spreadsheets or dense paragraphs of text, these diagrams let us visually track exactly when money is leaving our pockets and exactly when it's coming back in, clearly mapped across distinct periods of time.
Take a look at this. It brilliantly illustrates exactly what I mean. This is a real-world cash flow diagram for the Tiger Machine Tool Company. See that horizontal line? That's our timeline. Now, at year 0, pointing downwards in that pink bubble, we see an initial cash outflow of $75,000. That's our upfront investment. Then, pointing upwards in the yellow bubbles, we see the projected inflows: $24,400 in year 1, $27,340 in year 2, and $55,760 in year 3. Laying it out visually like this means we instantly grasp the project's timeline. But to actually compare all that future income to our initial $75,000 investment, that's where we have to mathematically apply the time value of money.
Which brings us nicely to Section 3, determining economic equivalence. To make that comparison, we use what I like to call our universal translator. We rely on 5 standard variables used in compound interest calculations to find economic equivalence. First, we have I for the effective interest rate per period. Then N for the number of compounding periods. Next is P, standing for the present sum of money, and F for the future sum of money. Finally, we have A, which represents a uniform series of cash flows. You can think of A kind of like an ongoing annual payment or an annuity. Literally, every engineering economy problem you're going to face will use some combination of these exact 5 variables to slide money back and forth along that timeline we just mapped out.
So it all boils down to mastering the difference between present worth and future worth. When we talk about present worth, or P, we are calculating the equivalent value of one or more future cash flows, but we're pulling them all the way back to our reference point today, year 0. Conversely, future worth, or F, is pushing present money forward to see its equivalent value at a specific reference point in the future. Depending on the exact decision you're trying to make, you'll use our translator variables to convert all of your mapped cash flows into either a single P value today or a single F value tomorrow.
Let's upgrade our toolkit a bit in Section 4, arithmetic and geometric gradients.
Let's start with the arithmetic gradient.
This happens when cash flows increase or decrease by a constant dollar amount each period. Just look at the data here. In year 1, the cash flow is $2,000. In year 2, it's $3,000. Year 3, $4,000. It is growing by exactly $1,000 every single year. To find the economic equivalence of a scenario like this, we mathematically split the cash flow right down the middle into two parts: an annuity base, which is that flat $2,000 every year, and the gradient portion, which is the $1,000 constant increase. By separating them, we can easily use our standard variables to calculate the total annual equivalent.
Now that handles flat dollar increases perfectly. But, sometimes things scale a little more aggressively. Sometimes cash flows don't just step up by a flat amount, they grow by a constant percentage rate.
And that is when we hit the geometric gradient series. Check out these data points. We start with a cash flow of $1,000 at the end of year 1. But instead of adding a flat $100 or something, it grows by a constant rate of 20% per period. So year 2 is $1,200, year 3 jumps to $1,440, by year 4 we're up to $1,728. Notice the curve on the right? Unlike the perfectly straight steps of an arithmetic gradient, a geometric gradient curves upward because the growth is actually compounding on top of itself.
Because it curves exponentially like that, calculating the present value requires a specific formula. The math depends entirely on whether your growth rate, represented by that little f with a bar over it, is equal to or different from your interest rate I. Now don't let the algebra freak you out. These formulas simply take that compounding, curving growth we just looked at and efficiently pull all of that future money backward to a single, solid present worth value at year 0.
Let's actually put this into practice with a business scenario. Here's a case study for Acme's new weight loss pill, Miracle Burn 360. Acme projects their first-year revenues will be a massive $1.1 million. Pretty great, right? But because they expect the product to really catch on, they forecast revenues will increase by 15% per year for the next 5 years. Because that is a percentage growth, boom, we instantly know we must use our geometric gradient tools. If Acme uses an interest rate of 20% to measure the time value of money, they would plug these exact figures into the formulas we just covered to determine the true present value of this product launched today.
All right, for our final step, Section 5, Real-World Bond Valuation.
Now, what is really fascinating here is the sheer scope of history and geography we're looking at. On the left, we have a vintage 1944 United States War Savings Bond. On the right, a news clipping detailing the purchase of an 85 million ringgit 1MDB Islamic bond in Malaysia from 2009 maturing way out in 2039. The political context, the historical eras, and the currencies of these two assets are wildly different. Yet, neutrally speaking as engineers and analysts, the economic evaluation of both is literally identical. Whether it's 1944 or 2039, evaluating a bond relies entirely on the exact same time value of money principles we've been building today.
So what is a bond actually worth? The commercial value of a bond is simply the present worth of all its future net cash flows. That's the whole secret. If you map it out on one of our cash flow diagrams, you'll see a uniform series of regular periodic dividends, which is just the face value times the bond rate, followed by a massive single future sum when the bond hits maturity and the redemption price is finally paid out. To find what the bond is truly worth today, you just discount all those future dividends and that final redemption price back to the present, using the bond's yield rate as your interest. It's basically the perfect real-world synthesis of present worth, future worth, and uniform series calculations.
Wow, we have covered some incredible ground today, from the tipping scales of inflation and earning power to drawing out visual treasure maps, all the way to calculating complex geometric growth and international bond valuations. So I want to leave you with this final thought. If you were evaluating a multi-million-dollar project today, how would you use these time value tools to ensure it's truly profitable tomorrow? Remember, a dollar today is definitively not a dollar tomorrow. But with this progressive toolkit we just built, you now have the exact formulas and frameworks to predict exactly what that tomorrow looks like. Thanks so much for tuning into this explainer and keep leveraging these insights in your own financial decisions.